Okay, so I've got a drum, rate of gyration, mass, starts from rest, block, falls down 3 meters. Okay, I want to find the speed at that instant. At that point, I push a brake on it, falls another 3 meters, and basically I want to find, uh, I want to find how much force I have to put on it so it stops after 3 more meters. Okay, so again, this is positions. It falls 3 meters, falls another 3 meters, starts at rest, goes to some velocity, stops at rest. So again, it's going to be energy on this because it's position and um, uh, position and velocity. So I'm going to start by drawing this guy right here, right? I've got an inner hub like this, and again, I've got a tension pulling down on this guy. Okay, I have, whoa, that's not what I meant to do. I have forces like this, where I've got mg pulling down on the drum, which is 50 times 9.8. I also have basically a pin joint, OX and OY, which is probably not going to be all that useful to me. Eventually, I'm going to have a normal force, okay, and then a friction force, which is going to be pushing down, because this thing is going to rotate counterclockwise, so that friction has to oppose that, so it's going to create a clockwise force on it, like so. So that's my free body diagram on that guy. Okay, so we just kind of know what force is. Now, really, the only thing causing rotation here is the tension, as well as the block pulling down on it, as well as the friction. Now, initially, the only thing really doing any work on it is the block falling. So let's go ahead and start. Let's do the first part. Okay, so start with the kinetic energy. The work being done on the entire system equals the weight. Okay, and that equals the final kinetic energy. Okay, so again, everything starts from rest. It says somewhere up there, this. Well, let's have to, starting from rest, there it is. Okay, so starting from rest, so that guy goes to 0. Now, again, initially the only work being done is gravity, right? So that gravity is going to be basically mgh, which is going to be 15 times 9.8, and again, it falls 3 meters. So the work being done initially is 44.1, or I'm sorry, 441. Again, at this point, friction's not being applied. All of those other forces are not causing any motion. The only thing causing motion is gravity pulling down on AB, which also causes rotation of the drum, which is where KE2 comes in. And KE2 is the kinetic energy of the whole system, which not only includes mv squared of the cylinder, okay, but it also includes the 1/2 I omega squared of the drum. Now, the drum is not translating, the cylinder is not rotating, so it's just the linear energy of the cylinder, the rotational energy of the drum, okay? But from this, I get, okay, 1/2 m, which is 15, that's of the cylinder, times the velocity squared, which is what I'm looking for to determine the speed of the block, okay, plus, not sure what happened there, plus 1/2 I. Now, I of the drum is going to be m times the radius of gyration squared, so that's going to be 50 times 0.23 squared, oops, that is I, 1/2 I, and then omega squared is equal to the velocity times that 0.15 around the outside, and that will all be squared. Okay, so again, this all is based on the velocity. Again, the rotation is related to the velocity by that radius of 0.15. So my kinetic energy is just a big old equation that just has V in it, right? My work is 441, so essentially that 441 has to equal that big ugly equation. And from all that, I can find the velocity at this point is 2.58 meters per second. Again, now this is before the friction is applied, right? So the work is just due to the gravity. Kinetic energy is both the kinetic energy of the drum and the block. Okay, I just have it's a single energy is still just a scalar equation. I have to include both rotational as well as linear energy in that. Okay, so now moving on to the next piece, right, where I have KE2, right, plus the work from 2 to 3 equals KE3, right? So this guy's coming to rest. I'm basically trying to figure out how much friction I need to place on this for it to come to rest after 3 meters. Okay. The other thing I know is from the above equation, KE2 is just equal to the work, which was 441. So I can say that KE2 equals 441 from the problem above. Now I've got the work being done. First thing I have here again is this thing falls another 3 meters due to gravity. So gravity does another 441. Oh, God dang. Amount of work on this. Okay. Now friction is going to be doing negative work. Again, gravity was doing positive work because the block was moving downward in the direction of gravity. Okay. Friction is going to do negative work. Okay, so let's, I guess, first figure out what the friction is. So friction is going to be the 0.5 times the n. So I just have to find n here. Okay, so if I find that, if I look at this guy here, and where am I going to draw this or write this? I'll just slide down a little bit and say that, okay, if I sum the moment about n, this is just a statics problem, right? Because this rod is not moving. So if I sum the moments around A, I'm going to have 1.25 times P minus 0.5 times n. And again, that equals 0 because the rod there does not rotate at all. Okay, so from there, I learned that n equals 2.5 p. Okay, so now I know that friction is going to be 1/2 of that, which is going to be 1.25 p, right? Because the friction is mu s times n. I know n is 2.5 p, so I know that the friction is that. So from that, I know that the friction force is 1.25 p, and at this point I just need to figure out basically how much friction that guy causes. Basically the arc length of that drum moving around it. Okay, which again, that is going to be r times theta, where r is 0.25, and then theta is that distance it falls 3 times the, or I'm not times, divided by the 0.15. Again, the block falls 3 meters. Okay, that one's wrapped around a 0.15 radius, right? So that guy, the arc length, I'm sorry, using the arc length, we can find the revolution to be 3 divided by 0.15. Then knowing that revolution based on how far the block falls, then on the outer edge of that drum, I take it times 0.25 to find the arc length that the friction acts over. Okay, so now all I really need to do is solve for P, right? So again, what I have here is I'll go ahead and write this equation. I have 441 plus 441 minus 1.25 p, that's the friction force, times its rotation, which is going to be r times theta. And again, that comes to rest at 0. Solving that equation, I find the P I have to apply up the top to get this to happen is 141 newtons, which will make that thing come to rest after 3 meters.